We're going to talk force applications today with respect to vectors. So we've got 3 examples, and I do have a 4-step process that you can follow, and it's very straightforward. There is some work that you have to do, but it's very straightforward if you follow the process. So in our first example, what force is needed to keep this rock from rolling down the hill? That is our question. Now notice that we are searching for W1. So consider the 400 pound rock on the hill with a 30-degree incline, as you see. If the force if F represents the force exerted by the rock due to the gravity, and V is the incline, that's the vector that represents the incline, then W1 is the projection of the force vector onto vector V, which is the incline. The magnitude of vector 1 is the force required to keep the rock down. So what we are ultimately looking for is the magnitude of vector 1. Okay? Now, the way this works, vector F, or for F, we're going to write a vector. Now, if we write a component vector, if you recall, component vectors start at the origin and then they move. So hypothetically, if you had the x and y axis, that force is going straight down the y axis. So that would be 0, negative 400. All right. Now, we're going to write a unit vector. Remember, unit vectors have a magnitude of 1. And so we're going to write a unit vector in the direction of the hill. So our vector V is going to be 1 cosine 30 degrees, because that's our angle, and 1 sine 30 degrees. Now the reason I'm using 1 is because it says write a unit vector, and the magnitude of all unit vectors are 1. So that's the length of my vector V. Okay, now this actually gives me, and I'm going to have to write it up here, square root 3 over 2 and 1/2, because I can pull that off of my unit circle, so I don't want to list the decimals there. So in the next step, we are going to actually find vector W1 by using the projection vector, and that is going to be the force vector dot product of the force vector and the vector, magnitude of vector V, and then we're going to multiply it by vector V. So when we go through to do this, and I'm only going to do this once because there is a shortcut and I will show you that. So when I do this, I'm going to get 0 times the square root of 3 over 2. I apologize, my pen didn't pick that square root 3 over 2 up. We're going to add that to negative 400 times 1/2. All of that is over the magnitude of V squared. So if this is a unit vector, the magnitude is 1, and we're going to square it. That is also what you would get if you did square root 3 over 2 squared plus 1/2 squared. If you took the vectors, you would get 1. Okay, so if you took your vector V answer right here and you went through the process of finding the magnitude of vector 1, it's automatically going to be, or vector V is going to be a 1. And then we're going to multiply that by the vector, square root 3 over 2 and 1/2. Now, here's the shortcut. When you do all of this, you get negative 200 times our vector, square root 3 over 2 and 1/2. When you multiply that out, you get negative 100 square roots of 3 and negative 100. That is W1. Now, when I go through and I actually find the magnitude of W1, and I do the square root of negative 100 square roots of 3 squared plus negative 100 squared, I get 200, which is the absolute value of this number right here. So instead of going through all of that, because it's going to work this way every time, if this is a unit vector, I'm going to multiply by that unit vector. So instead of actually writing this value down every single time and going through all those steps, negative 200 V is what I'm going to set W1 equal to. I'm not going to do this part. And then I am simply going to change that to a positive 200. It'll work that way every time. So it saves us a lot of steps, but if you need to see all those steps, by all means do it. You're going to get right back to where we started. Okay, so when we do step 3, this is what I want you to do. All right, so I kind of showed you how all of this works. So when you go to do step 3, what we're going to do is we are going to show 0 times square root 3 over 2 plus negative 400 times 1/2. And all of that is divided by 1. You don't even have to show that because we've already proven that the magnitude of vector v is a 1 and the square root, or when you square 1, you get 1. And we're just going to multiply it by v because we know v is a unit vector. So when it's all said and done, we're going to get negative 200v. Then I'm going to take that, so the magnitude of v1 is 200 pounds. So it's going to take 200 pounds to keep that rock from, 200 pounds of force to keep that rock from rolling down the hill. So that is the shortcut. So I've kind of showed you the full gambit, and we're going to continue to use that shortcut. Now, if you notice in example 8, I have all 4 parts already written down, first, second, third, and fourth. So what we're going to do is we're going to kind of look at our picture. So you have a 150-pound cart that sits on a ramp on an incline of 60 degrees. So here's your cart up here. It's a beautiful cart, I know. Okay, what is the force required to keep the cart from rolling down the ramp? So that would be 0, negative 150. Because remember, this is a component vector and it starts out of the origin. So there is like a makeshift x and y axis at that point where the vector starts. You don't see it, but it's understood to be there. For the second part, since v is a unit vector, we're going to do 1 cosine 60, because that's our angle of incline, 1 sine 60, and that will give us 1/2 square root 3 over 2. Now, here is where the shortcut kind of comes in. So instead of doing the full gambit, all we have to do is show our dot product, 0 times 1/2 plus negative 150 times square root 3 over 2. And we are going to multiply that by vector v. Now, vector v is a unit vector, so I don't really have to incorporate in this. I know it's going to turn out to be a 1. So when I do this, I get a grand total of negative 75 square roots of 3. All right, so my magnitude is just going to be 75 square roots of 3 pounds. That's the shortcut. Or you can multiply that out to 129.9 pounds, depending on what MathXL or your homework application wants you to do. All right. So in the last problem, we are going to apply the shortcut. So we have our ground, and Carly is pulling her brother on a sled. at a 12-degree incline. Okay, if the combined weight of the sled and her brother is 45 pounds, what force is required to keep the sled from sliding down the hill? So our force is 0, negative 45. Our unit vector V will be 1 cosine 12 degrees, 1 sine of 12 degrees. And for now, I'm simply going to leave that as cosine 12 and sine 12. That way I do not have to round multiple times. So that's what I'm actually going to plug into my vector 1, which is my projection of the force onto vector V. So what I'm going to do is my shortcut. That's going to be 0 times cosine 12 plus 0, I'm sorry, not 0, negative 45 times sine 12. All of that is divided by the magnitude of V, which is a unit vector, so that's divided by 1. And we're going to multiply by that unit vector. So when it's all said and done, I get negative 9.36 V. So the magnitude of that would be 9.36 pounds. All right, so if you have any question about force application, please contact me, let me know.